In this section, we will discuss how a calibration model being used by a lab can appear to be acceptable by the method criteria, but does not properly reflect the data. EPA Method 525.2 in Section 10.2.6.1 states, calculate the standard deviation from each mean. RSD equals 100 times the standard deviation divided by the mean. If the RSD of any analyte or surrogate mean RF exceeds 30%, either analyze additional aliquots of appropriate cal solutions to obtain an acceptable RSD or RFs over the entire concentration range, or take action to improve GC mass spec performance. In this example, a lab was reporting 2,4,5 trichlorophenol by EPA method 525.2. The lab was using an average response factor calibration model, which for this compound resulted in a RF relative standard deviation of 29.3%, which meets the method criteria. However, it is obvious that the quantitation line does not reflect the data very well, especially on the high end of the curve. If the lab had flipped the calibration model to linear regression, as is presented in the second curve, all of the calibration points are better represented and the method criteria is also acceptable. In EPA Method 8260B, Section 7.3.8.2, it is noted that Method 8000 specifies a linearity criterion of 20% RSD. However, Method 8000C in Section 11.5 also states, in addition to the acceptance criteria found for each of the calibration models, it is recommended that each calibration model be inspected to ensure that the data are representative of the model chosen. This inspection is described in Section 11.5.5.1. Section 11.5.5.1 provides a formula for refitting calibration points back to the model and determining if all points in the curve have an absolute value of the percentage difference of less than or equal to 20%. In this example, a lab performing EPA Method 8260B for analysis of acetone obtained a 15% RF relative standard deviation, which meets the method criteria. However, it is obvious that the highest standard has a saturated response and it is not well represented by the curve model. If the lab had flipped the calibration model to a quadratic calibration model, as shown in the second curve, the highest standard would have been better represented. However, because of the saturation of the highest standard and low increase of response ratio from the next lowest standard, this is not a good curve model for the data and may produce questionable quantitative data at the high end of the curve. Probably the best solution would have been to drop the highest calibration standard that was showing signs of saturation. The resulting curve without this high standard has a much lower relative standard deviation and represents all of the remaining calibration points well. This model, because of the higher weighting associated with the higher standards, may have lower calibration standards that are not well represented, but will still pass a method criteria as was demonstrated under the linear regression least square calibration model discussion. In the first example, which is also discussed under the detector sensitivity section, a linear regression curve was used for the EPA Method 552 analysis. The lowest calibration standard is askew from the other points, having more response than the next highest standard, but meets the method criteria. The quadratic curve fit used for CDBAA from the same analysis shows that this type of curve will also allow lower calibration points to be askew, but still meet the calibration criteria. In both cases, the lowest calibration point should have been eliminated. In this final example, we will show that a lab's analyst chose to inappropriately manually integrate a compound to make the calibration curve appear to meet the method criteria, rather than simply applying the correct calibration model. The first calibration curve shows the lab's original calibration standard data before manipulation, which shows a RF relative standard deviation of 21.1%, which fails the method requirement of 15%. The analyst inappropriately manually integrated the lowest calibration standard, adding area response not attributable to the peak that pushed the RF relative standard deviation to 11.4%, which appears to meet the method criteria. The real problem with the data is that it does not want to be forced through the origin. If the analyst had simply taken the original unmanipulated data showing the failing 21.1% RF relative standard deviation and flipped it to a linear regression model, it would have passed the method criteria of 0.995, and the data is much better represented.